Welcome. This lesson marks a shift. You know the basics: loops, functions, vectors. But there's a gap between code that compiles and code that's actually good C++. Pointers and references are where you close that gap. By the end, you'll understand how references create aliases, how pointers store addresses, when to use each one, and how to avoid the bugs that trip up even experienced programmers. This is intermediate territory. Let's get into it.
A reference is an alias,
Another name for an existing object. We declare int value equals 10, then int &ref equals value. Now ref and value refer to the exact same object in memory. When we write ref equals 20, value becomes 20. There's no copying happening. They're the same piece of memory with two names. References must be initialized when declared. You can't create a reference and point it at something later. And once bound, a reference can never be reseated to refer to a different object. These constraints are what make references safe. They're always valid, always bound, and always refer to exactly one thing.
A pointer is a variable that stores
A memory address. We declare int value equals 10. Then int star ptr equals &value. The ampersand operator takes the address of value. Now ptr holds that address. To access the value through the pointer, we dereference it with the star operator. Star ptr equals 20. This follows the address and modifies the object it points to. Unlike references, pointers can be null, pointing to nothing. They can be reassigned to point at different objects, and they can be involved in arithmetic. This flexibility is powerful, but it's also the source of most pointer-related bugs. References are constrained by design. Pointers give you freedom and responsibility.
a pointer can be null,
Meaning it points to nothing. In modern C++, always use null, not the old null macro or zero. Null Peter is type-safe and unambiguous. Now the key question: when do you use a reference versus a pointer? 3 rules. First, use a reference when the object is required. A reference can't be null, so it guarantees the caller provides a valid object. Second, use a pointer when the object is optional or when you need to reseat. Point at something different later. The null state lets you represent absence. Third, use a smart pointer when you're expressing ownership. Unique pointer for sole ownership, shared pointer for shared ownership. These 3 rules cover the vast majority of function signatures you'll write.
function signatures in C++,
Communicate contracts. 4 examples. First, void rename, taking string reference name. The reference says this function will mutate the object and the caller must provide a valid one. Second, void print, taking const string reference name. The const reference says this function will read the object but won't modify it. Third, void maybe use, taking const widget pointer. The pointer says the object is optional. The function will check for null before using it. Fourth, void take owner, taking unique pointer to widget. The unique pointer says this function takes ownership. The caller gives up the object. Each signature tells a different story. Learn to read them, and you'll understand any C++ API at a glance.
let's see the difference in practice.
The reference version, void increment, taking int reference x, then ++x. The caller must provide a valid integer. There's no null check needed. The reference guarantees a real object exists. The pointer version, void increment if present, taking int pointer x. First we check if x is not null. Only then do we dereference and increment. The pointer version handles absence explicitly. Use the reference version when the argument is required. Use the pointer version when the argument is optional. This isn't just a style preference, it's a contract. References say required. Pointers say maybe. 3 categories of pointer bugs you must learn to recognize. First, dangling pointers. A pointer that points to memory that's already been freed. The object is gone, but the pointer still holds the old address. Dereferencing it is undefined behavior. Your program might crash, corrupt data, or appear to work fine until it doesn't. Second, double delete. Deleting the same heap object twice. This corrupts the memory allocator and leads to unpredictable failures. Third, use after lifetime ends. Accessing an object through a pointer or reference after the object has been destroyed. This includes returning references to local variables and holding pointers into reallocated containers. All 3 share the same root cause. Something changed the lifetime of an object, but the code using it didn't know. 2 concrete examples of lifetime bugs. First, a dangling reference. This function returns a const string reference, but the string it refers to is a temporary created inside the function. As soon as the function returns, that temporary is destroyed. The caller receives a reference to dead memory. This is undefined behavior. The fix: return by value, not by reference. Second, pointer invalidation with vectors. We take a pointer to the first element of a vector. Then we push back a new element. If the vector needs more capacity, it allocates new memory and moves everything. Our pointer now points to the old, freed memory. This is one of the most common real-world pointer bugs in everyday container code. The fix: don't hold raw pointers into containers across operations that might reallocate. This is the most important mental model in modern C++. Every pointer and reference falls into one of 2 categories: ownership or observation. Owners manage the lifetime of an object. Stack objects own automatically. They're destroyed when the scope ends. Unique pointer owns a heap object exclusively. Shared pointer shares ownership when multiple parts of the code need the object to stay alive. Observers just access the object during a call. References observe required objects. Pointers observe optional objects. Span observes a contiguous sequence. String view observes text. The critical rule: observers must never outlive the owner. If the owner destroys the object while an observer still holds a reference, you get undefined behavior. In modern C++, most pointers and references are observers, not owners. Const is your most powerful documentation tool. When you write void print, taking const string reference text, you're making 2 promises. First, the function won't modify text. Second, anyone reading the signature knows this instantly. When you write void mutate, taking string reference text, no const, the signature says this function may change the string. The compiler enforces these promises. If print tries to modify text, the code won't compile. This catches bugs at compile time instead of runtime. Apply const to every reference and pointer parameter that doesn't need to modify the object. It makes your code safer, clearer, and easier to reason about. Const correctness isn't optional. It's one of the defining practices of good C++. Modern C++ provides safer alternatives to raw pointer patterns. Instead of passing a pointer and a length, To represent a contiguous range of integers, use span of const int. Span knows both the start address and the size, so bounds checking is possible and the interface is cleaner. Instead of passing a const char pointer for read-only text, use string view. It carries the pointer and the length together, supports all the string search and comparison methods, and makes the non-owning contract explicit. Both span and string view are lightweight. They don't copy data, they just provide a view into existing memory. But remember, views don't own the data. The source must stay alive as long as the view is used. These types replace the most common raw pointer patterns with safer, more expressive alternatives.
Here's your quick reference for choosing between pointers,
References and modern alternatives. Required object, use a reference. Optional object, use a pointer. Owning a heap object, use a smart pointer. Unique pointer for exclusive ownership, shared pointer when truly needed. Non-owning contiguous sequence, use span. Non-owning text, use string view. These 5 rules will guide the vast majority of your function signatures. For next topics, continue with classes and structs to learn how to define your own types and organize data with behavior. Then, memory management to understand how smart pointers and RAII manage object lifetimes automatically. Pointers and references are the connective tissue of C++. Now you understand what they mean. Thank you.